Alright, the very good morning, good afternoon, and good evening, and good night, of course, to all of you. So, today we're going to continue back with the next chapter. So, our focus for today will be on chapter number 7. We will talk about the functional form and the logarithm. So, what is functional form and logarithm? We will discuss that in the next at least about minutes to come, talking about functional forms and logarithm. So what's the menu for today? The menu for today will be two parts. One will be talking about the functional form, the other one will be talking about the logarithm, especially in econometrics. When you say logarithm, means that the decision of whether we have to take log of the variable or not. So that is what we're going to do today. And this logarithm also very much related to the functional form, which we're going to discuss here, right? Basically, so a review before we go into the basic chapter will be on regression with constants. So normally we have this sign, either we written in alpha or written in beta 0 in this example. Although it do not the intercept do not have economic meaning, but it do not have meaning, but then we normally, when we estimate, we put the constant term. Even if you when I show you in the next few videos about the estimating using the EViews econometrics view, even the program itself have the constant when you do the regression. So this is a important elements inside when we do the regression model. That's why we always write y equal to alpha plus beta x. Alpha, the constant term, right? Should not be eliminated inside the regression function. Right, so this chapter basically is from the few pages from 159 onwards. Let me show you the pages in this particular book that we are using, especially what we call Gujarati and Porter, right? Let me go through the section here, 159, all right? So if you see this Gujarati and Porter, which is under chapter number 6, so this is the functional form that mentioned about, especially for this particular chapter. So we're going to focus on the few here, especially example that given here, the log linear, and then the semi-log is actually also considered as log linear. You have log linear, linear log, log linear, linear log is already two different model, and then we have reciprocal here, this reciprocal model, and then the logarithm model without the reciprocal. And we will consider also another model which is called the linear model. That's what we are going to do in this particular chapter itself. So basically, this is what we're going to discuss. So we have 5 different model. First one you call linear model. Yeah, we are doing linear model at the few chapters already until now, right? So and then the focus will be mostly regarded to what we are talking about here, right? Basically, and surely that you need to know that based on what we have discussed here, will be 5 different model. One is the linear model, again, repeated back, linear model, double log model, semi-log is required the 2 different setting, one linear log, one log linear, and inverse reciprocal. Right, so linear model is what we are doing for the previous few chapters until now, right? Until the previous chapter, this is what we estimated. This is called multiple regression, right? We have multiple x there. The x's are multiple there, and this model have a slope of a constant slope, right? Have a linear, have a constant slope, because we use this line to represent the population, right? And this line, this slope itself, we can calculate the slope of this particular line, and the slope is actually constant over the sample period, right? Over the sample, right? So the elasticity in this case also with respect to the y is considered as not constant, right? Is here we reverse the elasticity is actually the point elasticity, which have different value for x, ji and yi. In this case, we are talking about that the elasticity of the coefficient actually are not the same. Surely they are not the same, because surely they are different in that particular sense. All right. So here is a very strong indication. Linear model may be estimated using OLS, right? All the other models too. Linear model should be used unless strong evidence that is inappropriate is found. So the first function here is to let you to let everyone knows that we have 5 different functional form, 5 different model that we can estimate, which produce 5 different answer, 5 different result and the coefficient. And the question is that which one is the most suitable one for our estimation. So that's the job here to do, especially in your project and maybe later on in your FYP. Which model that we should, which functional form that should we use? So we have a choice of 5 different model, and then from there we choose one. How are we going to do that? That's what this chapter is all about. All right. The second model there, we'll be talking about double log. When you say double log, that means that both sides are log, logarithm, taking logarithm, right? Here, when you take double log model, it's non-linear in variable but linear in coefficient. Non-linear in variable, so the variable can be a non-linear relationship in that particular sense, right? But the coefficient that you get will be linear itself, right? So here the elasticity of the model are constant comparatively to the one just now. The linear model are not constant. Elasticity are constant, but the here the elasticity, sorry, the linear model says that the elasticity are not constant, but the slope are constant, right? So in that particular scenario, the double log model is also known as constant elasticity model, because the elasticity itself will be interpreted, the coefficient will be interpreted as elasticity. But not in the linear model, right? The interpretation do not represent elasticity. That's why they are not constant in that sense. All right. So we move forward to another model in that sense. Before we go in, this is the transformation of what we have. So use the natural log when you do that, both logarithm, and certainly it can be estimated using OLS. OLS will recognize, the method will recognize such the data that you put into eViews, right? Double log model. This is called double log model. Constant elasticity, for example, like this. Right, this is the original one, and after you log, you get something like this, for example. Okay, so again, this is the other example of how the constant or double log model looks like. All right, semi-log, you have two sides of the coin. One is called log linear. We will start with that first. All right, log linear model has a log form in the dependent variable. Here you have log, but here you don't have. Here it is linear. So this one is called log linear, right? The coefficient, the linear side will be in the coefficient of the x, and the y here are taking logarithm. So looking into that perspective, looking into this perspective here, it says that the slope is not constant, but the elasticity of the is also not constant. So both are not constant in this sense. The reason behind, again, why we use this type of model, why use log linear model? We should use when the impact of x on y is hypothesized to be increasing at the increasing rate, decreasing at the increasing rate. Log linear is applied to a situation whereby y adjusts in the percentage form of the unit change of x. Right. For example, in this example here, the salary of workers rises as the percentage of his or her previous salary x year. Right. Also be used as a growth model. You can see the example there in Gujarati and Porter. Let us see that in Gujarati and Porter here, the book itself. Let us go to the book where we have an example of a linear log at the page 1. Yeah. Here is a log linear example. So we use that for to measure growth rate here, to measure the growth rate, the example here, right? In that scenario, we call it certainly call it semi-log. So this is the example there. I mean, the other example of a log linear model. Right, this example, example 6.4 here, the rate of growth expenditure on service is the good example. You can always refer to this and talking about how it can be easily interpreted in that sense. Right, so we have log linear model in this sense. Let us go back to the notes. All right, the next model will be linear log. Again, if you want to refer to the example in the book, there's always there. And the other book which I recommended will be the Econometrics for Dummies, which has also the several examples there. But referring to the book Gujarati and Porter is pretty good enough. Right, linear log on the other side of the coin, compared to log linear just now, as a form of a log in the independent variable. So now it's different. This side is been logged. This side is not. The y is not. So here you have the slope is constant. Sorry, it's not constant also. Both are not constant, both sides. Both not constant, and the elasticity also not constant. Same scenario as this, but when to use this? This one is the other way around. Just now, if you see that increasing at increasing rate, decreasing at increasing rate, here is increasing at decreasing rate and decreasing at decreasing rate. So this one is rather confusing, but then again, you always can refer to Gujarati and Porter of how it been applied. So this is one example here. Consumption increase with the decreasing rate with the respect of income, or we should apply the total utility theory. Consumption increase, satisfaction increase with the decreasing rate. It's like when you are saying the satisfaction of drinking a cup of water is very satisfying at first. Second cup of water is still satisfying. Third, fourth, fifth, your satisfaction might reduce in terms of utility. Right, still satisfied, but not as satisfied as the first cup of water. So that kind of example can be used for linear log scenario. Let us go here as the example here. It written here linear log, unlike the growth model. We use the type of different types of this one is the example of expenditure. You see here total expenditure, and then you have revisit the example of food expenditure in India using linear log kind of a model. Right, this is the example here. You read on the box here inside the example of 6.5 at page 165 to be more detailed as the given this example. All right, let's go back here again of what we are discussing. The last model there, the model number 5 that we're going to share with you in this particular video will be on the reciprocal. What is reciprocal? Reciprocal is you express is a function or inverse as one or more of the x variable. Yeah, in this sense, rather than you have x itself, we have 1 per x. Right, the slope is not constant, elasticity also not constant. So you express the just one of the variable. The x2 are still the same variable. Right, the same variable. Linear, this is linear, but this is reciprocal. Right, when to use this type of model, the example given actually in Gujarati and Porter is about the Phillips curve. Phillips curve is the relationship between unemployment and inflation in that particular sense. Comparatively, the reciprocal model here A, and then the linear model. So there are two different models to represent here. See here, this is the reciprocal. Here is the linear model, linear function model. Right, so this is the summary of the 5 different models that I just introduced to you. The linear model, we started off with linear model, and when we have double log model, we have linear log or log linear, and then log linear, and then reciprocal. We do not discuss on polynomial. Not in this particular video here. These five options of functional form is good enough to know when you want to do the modeling process of the econometric project, especially to choose which one is the most suitable one for your model, for your variable. So here, the next few slides will be about the estimation that I do to enhance the understanding here on the variable here on GDP and M1. GDP and money supply 1, and this is a result of 5 different model. Right, result of 5 different model. The first model here is the linear model. Second model, double log model. Look at the result and the variable. They are totally different. Right, if I summarize down, they're totally different. So here's the double log model. Here is the log linear model. Log linear model. Log at the y, linear at the M1 side. And here is the linear log model. Right, linear log model. You see how the coefficients are different. The coefficients are different here, 1.628, here are 1.318 for the M. Here is 0.002. Here is 727 for the log, linear log model, and reciprocal model produce these results. Right, so five different models that estimated produce 5 different results. So the question again is that which one will be the most suitable functional form? So that's what we are getting into, the choice of functional form, right? Which model that you will need to choose. So for the project, especially for the project for this particular class, is that the group need to estimate 5 different model and choose the best model that is more suitable for your function, for your project itself, right? And then you need to explain the steps, how we're going to do that. So that's why this chapter itself is particularly important, especially this first part, the functional form. So in our regression model, if wrong functional form is estimated, we committed specification error. Remember back this A1 and A. What is this A? Is this when we talk about the assumption number 1 and assumption number 9, and the test that very pretty much related to us in this particular specification error will be Ramsey reset, which I do introduce in the chapter number 6. Right, again, I have not shown all of you on how to do it in eViews. We'll do that in the next few videos. Right, estimated results are invalid, means that if the result different functional form or wrong functional form and not suitable for forecasting, surely if it's here are not the result are not invalid, certainly is not suitable for forecasting. So the choice of it, there are few rule of thumb that we can follow. The rule of thumb that you can follow on this particular sense. Number 1 here is we use information criteria. This AIC, AC, and FPE. AIC is a Kaiki information criteria. Right, here is Swatch criterion, and FPE is a final prediction error. This is just how we choose which one will be the best model based on this indicator. This if you see here, there is AIC here. This is AIC. This is SC. This is SC. We don't have here in this result. We don't have the FPE. So that's the criteria here. We're not going to use this as a criteria choice to choose the model. Just to introduce you what is available for the choice of functional form. Some would use this as the example, as the criteria to choose the best model. Root mean square error, RMSE. This one is based on forecasting. Here the result do not show the forecasting, means that you need another step to show that the forecasting of this particular variable of the forecasted GDP, right? Again, can be shown to you in the eViews. When you do that, all of this is available in eViews. It's just that you need to click appropriately and know what is happening. The number 3 day, which we could do certainly on this part, which we will do throughout this this course, will be on the residual diagnostic. That's what we're going to do in the second part. After we estimate, then we need to check, to test whether the model is normal, for example, whether the model passed the Ramsey reset, whether the model is stable, whether the model is free from autocorrelation, whether the model is free from heteroskedasticity problem, or whether the model is free from multicollinearity if you have multiple X in the model. Right, so this is one that can be done, right, to know whether they are normal, using the error term are normal using the Jacques-Bera test and Ramsey reset test as a part of a functional form. And number 4 here is pretty much related to number 3 and number 1 that I just mentioned, the supplement of chapter number 6, which you've done in the previous videos before this, right? So Ramsey reset test is a test that to know whether you choose the right functional form, right? You can do that. So, and this is the method that I'm going to introduce to you here in this particular video, what we call as coefficient of variation, CV in short, right? So, how to choose the best model of all the 5? How to choose the best model? This is the formula of it. The formula says that it measures the average error of the sample regression function of the standard error of the regression relative to the mean dependent variable. So very straightforward. This is standard error of regression. This is mean of dependent variable. You divide that. The smaller the value of CV of the model, the more preferred one, the more preferred functional form. Can easily compare between all the 5, meaningfully compare between all the 5 models just now. So again, remember back just now the result that I just showed you from the previous slides. So which one would be the most suitable one? We're not going to do this in the video here, but for the when we enter this particular chapter in the online class, we will do it. Choose the best model. You calculate it, and then you need to inform me which one will be the best model among all this. Where we do this. So 5 different models. 1, 2, 3, 4, 5. And then you need to calculate this CV, and then you need to choose which one will be the best. That's one. And then you can do this also using the residual diagnostic. That's what we can prove it to be. That's the best model. So pretty much that we're moving into the second part of this particular chapter, and the video part will be on logarithm. So how can we use linear estimator to fit in a nonlinear relationship? How can we do that? The question is that we do something nonlinear before we plugging into OLS, because OLS do not care or do not know actually where X and Y come from. This one is pretty much true. You can put anything into the program. Estimates, it doesn't mean that you will get some meaningful results. So the X and Y, the variable choice there is important, whether it's in a percentage, whether it's an index, whether it's a number, and so on and so on and so on. So again, that's why reading back the literature is pretty much important. So there are number 6 here, which is not written, is that you can always refer back to the literature to know whether what variable should be used, what types of model that most of your literature use. Are they using double log model? Are they using linear model or log linear for you to decide? That's one rule of thumb indication, other than calculating the CV, other than using the diagnostic test. Right? That's one a good way of doing it. Right? Refer back always to the literature. The literature is always be the ultimate guide for any researcher, right? Then again, you have to compare not just one research, but the numbers of research to come out with a conclusion. Says that these are the variable used, these are the methodology used, these are the whether they take logarithm or not. So that's the second part of it, logarithm in econometrics, right? So we can plug in this figure directly. We can do stuff. We can do something to it. So what we can do what we can do to fit in the curve is logarithm. We regress like this. This will be like, for example, the earlier example on double log model. Sorry, this is actually not dog. This actually is log, log also. So it's double log model. So we log both sides of x and y, so that we can fit in the nonlinear relationship into the linear function. So that's the interesting part here. All right. So after we take logarithm, actually, if both side logarithm, if you follow earlier just now the double log model, actually, after we log both, it actually called elasticity. Right? It's actually becoming the coefficient becoming elasticity. So the interpretation is actually pretty much of what we understand, what we call about as a elasticity. So taking logarithm of both x and y let us to estimate the elasticity. So from there we can easily talk about whether it's elastic or non-elastic, that which is pretty much related in economics also, economic studies. Here, for example, this is one example, the Phillips curve example. Again, it's a relationship between unemployment and inflation. Here, supposed to be I. Pretty much interesting. Come out like a D there. The data suggests a trade-off between inflation and unemployment. This is the relationship. You get the beta. This is the constant. This is the beta 1 represented by inflation before log. How do we interpret? We interpret that if the inflation, the number of best guess unemployment will be 0.06 percentage point. This is what you interpret in the linear model, right? A 1% point increase in inflation decrease the unemployment level by 0.05. I mean 0.55. Sorry, 0.55 here. Negative relationship, right? Because normally Phillips curves have negative relationship, right? So pretty much that is result before the logarithm, and this is pretty much almost similar as what you see in the that you will see in EBE's program. Now after, if we take both sides, logarithm, unemployment and inflation, then we can predict the percentage change, because now we become elasticity rather than percentage point, is percentage change. All right, percentage change are non-linear actually. It's like what is when we talk about growth rate rather than just percentage point. All right, this is percentage change. There are changes there. So changing inflation, for example, this is I put up it's red because it's rather important. You can always refer back to this video again to repeat to understand what I'm talking about here. So changing inflation, for example, from 0.01 to 0.02 is actually 100% increase. But changing inflation from 0.02 to 0.03 is only 50% increase, right? Here is 100% because it's this percentage change. But changing here is only 50%. So that's a two different. Although we increase 0.01, it means something else. If it talks about percentage change, but we talk about just point change like this, then will be the interpretation will be very straightforward. So remember that when you interpret double log model, especially and talk about elasticity types of relationship. So here, after logarithm, after taking log, then the result totally change compared to here. Right, here you have 0.55 negative. Here we have negative still, but it's 0.29. It's a different or if it's put up to the 2 point or 2 decimal point, it becomes 0.3. This is the new result after logarithm. So 1% increase in inflation leads to 0.3 percentage change in unemployment. Again, do not confuse percentage point and percentage change. Right, here for example, and inflation 15%. If inflation is 15%, 10% point change will move inflation 25 to 25%. That very straightforward. But if it's inflation is 15%, a 10% change move only inflation to 16.5 because it's only 10% changes, right? Percentage change in that sense. So it's different interpretation. All right. So pretty much, if this is the example, you have to be very careful with the interpretation, especially it talks about percentage change and percentage point change. The totally two different interpretation. Okay. So always can refer back to these particular videos again to understand again it more clearer. Or if not, we're certainly going to discuss this again in our online meetup for this particular chapter. Right. So with this, I'm going to end up this particular chapter with thank you very much, and then I'll see you. Adios and bye bye. Take care, everyone. Ciao.